The first governing equation we will look at is the differential form of mass conservation. And to show you where this equation comes from and what it looks like, I'll go back to my infinitesimal fluid particle moving within a channel. I'll assume that the density is constant. This is called an incompressible flow. And due to conservation of mass, the mass of the particle cannot change. And if its density is constant, the implication is that the volume cannot change, because if I take the density and multiply it by the volume, I'll get the mass. So with this assumption, mass conservation reduces to the volume of that infinitesimal particle cannot change. And let's say at time t, the dimensions are delta x and delta y. So that's the x direction, and that's the y direction. And at time t, let's say that the velocity of the left edge is u, and the velocity of the right edge is slightly different. Okay, so the right edge is moving slightly faster than the left edge, and its velocity is u plus delta u. And in reality, you're going to have this edge is going to move with respect to that. You're going to get skewing and so on. Right now, I'm looking just at one effect, the stretching in the x direction. So after a small time delta t, this has moved with respect to that, and it's moved with respect to that by an amount given by the relative velocity times the time increment. So the original dimension, let's say, was somewhere over here. So that was the original dimension. So essentially, what's happening is that the fluid particle is getting stretched. And this velocity here can be written in terms of this velocity can be expanded through a Taylor series expansion. Okay, so this is the first term in the Taylor series. So if I know the rate of change of the u velocity, which is the velocity in the x direction along x, then I can figure out what the delta u is, and I'll get the higher order derivatives and so on, which are going to drop out in the limit as delta x tends to 0, and I'm also going to assume that delta y tends to 0. So this is the key here, okay? And also delta t is tending to 0. So this also tends to 0. Okay, so you have delta t also tending to 0. Pardon my chicken scratch. And this means that delta u is given as the gradient in the x direction times this distance delta x. Okay, let's bring in a second effect. So now I will assume that at time t, not only is the particle stretching in the x direction, it's also stretching in the y direction, because this edge moves with respect to that, since its v velocity is slightly different from the velocity here. And so this distance here, okay, the amount by which it's stretched, is given by how much, that relative velocity delta v times the time increment. So it's analogous to that. That means the change in volume from time t to time t plus delta t is, okay, I take this and I take this and I multiply them. It's just rectangular. And the original volume is that. So that's the original volume. And then if I multiply through, when I multiply delta x, delta y, that'll cancel out. So I'll get, I'll multiply that by that, and I'll multiply that by that. And then I also need to multiply this term by this term, but that's going to give me a term that's delta t squared, and that's going to drop out in the limit as delta t tends to 0. Okay, so that's going to be a higher order term, which I can neglect, and I'm left with these two terms over here. And then I can write this in terms of the derivative. So delta u, we saw previously, can be written as du dx times delta x. That's what I've done over here. And similarly, delta v can be written as dv dy times actually delta y. Okay, dv dy times delta y. And the higher order term will cancel out because it's of the order of delta t squared. So now if I take the volume change and divide it by delta x delta y, which is the original volume, and divide it by delta t, which is the time increment, what this is giving me is what I'll have left if I divide through. So I'm dividing this whole thing through by delta x delta y delta t, and the left hand side then becomes volume change per unit time. So that's the rate of volume change per unit volume. And on the right hand side, I'm left with du dx and dv dy. And that has to be 0 if the volume of the particle cannot change. So I get my mass conservation equation, du dx plus dv dy is equal to 0. This is due to stretching in the x direction. This is due to stretching in the y direction. In fact, what this is telling me is if the fluid particle, if my infinitesimal fluid particle is stretching in the x direction, it has to shrink in the y direction. In reality, you know, this point here is not only going to move in the x direction with respect to that point, it's also going to move in the y direction. Okay, its y velocity can be a little bit different from there, and this edge is going to skew. Similarly, this edge is also going to skew, and we haven't accounted for that volume. It turns out that's a second order effect, and in the limit, as you know, delta x, delta y tend to 0 and delta t tend to 0, that effect drops out, and the volume change is purely due to, in that limit, is purely due to stretching or shrinking. So that gives you a sense of where the differential form of mass conservation comes from, and you know what are the physical principles embedded within the terms in the equation. We'll move on to looking at the differential form of momentum conservation next.